Now we will come to problems of the kind that we will encounter when we derive our equations. So let us find variations of f, c, j, etc. Due to variations in the displacement delta u. So you remember in our finite element equations is the primary variable that we solve for, and you can think of delta u as an error that we make in u. It's a function of x, y, and z, and due to this error, what would be the errors in f, c, and other kinematic quantities? That's what we are trying to see. So let's start with f and go step by step. So we want to find f. We know f is this, where this, remember, is del capital X, and we want to find the first variation of f in the direction of delta u. So we want to find first variation of f with respect to u in the direction of delta u. This is what we want to find. And then again use the basic definition of this. This is dd epsilon equal to 0 of f u plus epsilon delta u. So this is where we have used the definition of the directional derivative in the direction of delta u. Now so now concentrate on this quantity. We know that f is this, so f u plus epsilon delta u would be I plus gradient of u plus epsilon delta u. And this gradient, we know it's commutative, so this would be I plus gradient of u plus epsilon gradient of delta u. Again, remember that you can take gradient of delta u because delta u itself is a function of space, so you can take the gradient. So this is what f becomes. You take dd epsilon of this. This is not a function of epsilon, neither is this. This has an epsilon here, but that goes away and you are left with. So this comes, here comes our first important result, which is delta f is equal to, we know that these operators are commutative, so this can be delta of gradient of u. So this is a first important result. First variation of f inverse can easily be found. So let us erase this. So first variation of f inverse, to find that, we start with f inverse equal to 0. Delta operates in the same way as d does. So delta of these kinds of product functions would give you del f inverse plus f del f inverse, which is what you want to find. This is equal to 0. So del f inverse would be f del f inverse will be equal to minus del f inverse, which means del f inverse is minus f inverse del f inverse. Now we know that del f is already, we have found that del f is this. So this is minus f inverse so I have used the result for del f times f inverse. Now we have to now look at a characteristic of this kinds of quantities which have f inverse, f transpose, f multiplied with them. So so if you write this in indicial notation, you would write this as del del capital X. Say you are writing the ijth component of this, you would write it as um, you would write it as, so ik of this times f inverse kj. So this is the ijth component of this whole thing. So now this we know is del ui divided by del capital X k. So ik nabla 0 delta u ik is this, and then you have f inverse kj. But then f inverse kj is f inverse kj is del capital Xj divided by del capital Xk divided by del small xj. So it's the inverse of the it's inverse of the deformation gradient. So you're going from small x to capital X, and this is your inverse deformation gradient. Plug that in. So you have del ui capital Xk times capital Xk small xj. So here what you can see is k is the repeated index. So this is like del ui del capital Xk times capital Xk capital X small xj. So this is like the chain rule because there's a summation over this k, and this will boil down to del ui by del small xj. So this is the ijth component of this quantity, and this, as you can see, is the gradient with respect to small x. So that means that this whole thing is actually gradient of delta u in the spatial gradient of delta u, which leads to the final expression that del f inverse is f inverse times the spatial gradient of delta u, which is the direction in which you are taking the directional derivative. Now let us come to C. Remember, C is F transpose F. Okay, and we want to take delta Z. Again, use the product rule. So delta F transpose F plus F transpose delta F is what we get. We know delta F. So delta F is this transpose F plus F transpose. This is what we have. Now we have to know a few things about this, which we know. Let's recall them. So in indicial notation, if I want to write the ijth component of this, as I did in the previous problem, I would write del capital X j of delta ui. Often we treat this as a vector, which is actually an operator, but we do treat this as a nabla operator, nabla 0, and this is the jth component of that. So when you do this, when you convert these kinds of quantities to the indicial notation, remember that the j comes first. So we write the j first and then delta ui. We don't write delta ui nabla 0j. So that is what we probably should do if you are without abuse of notation, but we don't do it. So the j comes first along with the nabla 0. So that's what I have written here. You have to remember this. Now, remembering this, we can actually take this expression and simplify it a little bit more. So let's write C as F transpose F, and then del C is del F transpose F plus F transpose del F, and we have shown that del F transpose is nabla 0 del U transpose F plus F transpose nabla 0 del U. Write this in indicial notation. So you have del Cij is equal to del 0 of delta U transpose, let's write it as Ki and F Kj, plus F transpose, let's write it as Fki and Kj. So this is what we have when we write it in indicial notation. And this will become so remember the second comes first, second index comes first, so this will be del 0 I delta uk f kj plus fki delta 0 j delta u. Okay, so this is what we will get. Right now, here we will use another trick. So delta 0, let's say delta 0 I is equal to del x capital Xi, which can be written as del small x k by del capital Xi using the chain rule, and this is del xk times fki. So from here what we see is del 0 I is equal to or we write it in vector notation, so del 0 is equal to f transpose del x del small x or f transpose nabla. Okay, so this is what we are going to use now. So instead of these del zeros here, so del 0 uk, we will use this expression. So we will write this as f, let's say mi f mi so from here, so this is fki nabla k. So we'll write this as fmi lambda m del uk fkj. This will be written as fki times this is again fmi lambda m, sorry, fmj lambda m, this is j here, fmj lambda m. So if you now rearrange and here both m and k are repeated indices, so I can change m to k and k to m. So I'll make this m, make this m, make this k, make this k, and then I can take fmi out. I have so what you can see here is I have this quantity here, which should look familiar to you. So it should look familiar because we had earlier defined the small string tensor epsilon ij, which was half del ui del xj plus del uj del xi. So if you take delta of this, delta of epsilon ij, you will get half. Remember, delta is commutative, so you have del x j of delta ui plus del x I of delta uj, which is exactly similar to what you have. This is your nabla j, and this is your nabla I. We have switched from nabla 0 to nabla, so we have switched from the material gradient operator to the spatial gradient operator, and this is going to be your delta epsilon km or mk. We had m here and kj here. Sorry, at kj here. So let's write it as mk, delta epsilon mk. So what we have, or twice of that, because there's a half here, 2 delta epsilon mk, and let's write it as f mi 2 times fmi delta epsilon mk fkj. So finally, we have the result that delta of C is equal to 2 times F transpose delta epsilon times F. Okay, so this is what we have. So once we know delta C, we can use the same trick, that is C inverse equal to I, as we did for F, to find delta C inverse. So I leave that as an exercise for you. The result is given here. Now let us concentrate on J equal to det F. Now in order to find delta J, which is a function of u and delta u, we'll have to use two results that we have learned so far. First, we have now a scalar function J, which is a function of F, which is implicitly a function of u, of det defined as det F, which is implicitly a function. So we want to find the derivative of J in the directional derivative of J with respect to u in the direction of delta u. This is what we want to find. This is what delta J is all about. Now here J is an implicit function of u, and we will have to use the chain rule for this. So when we do delta J, we'll have to use the chain rule. What we have is, from the chain rule, if you go back to the chain rule, we'll have to take derivative with respect to f of determinant of f in the direction of f. So we have to take this in the direction delta u with respect to u, but we know this already, that this is equal to del 0 to u. So what we have to calculate is in the direction of. Now this we have done before as well. So remember, we had calculated the directional derivative of tensor A in the direction of t, and this came out to be det A times det of A in the direction of t. This came out as det A times trace A inverse t. In this case, t is this tensor. This is your t, and so this quantity will now be equal to det F times trace of F inverse det f is j, so this would be j trace of F inverse. Okay, so again F inverse nabla 0, this is a ripe quantity for transformation into the spatial gradients. We can do that easily. So let us write trace of F inverse is to be equal to F inverse times I. This is the trace, and we write this in indicial notation. So this would be del capital X So what I'm writing is for this, I am writing the mjth component, and mjth component, the j will come first, m will come next. So then I have delta j. So this will become del xi of the j will knock off the I times dum, which will become del capital xi del small xm times this quantity is del capital xi. So these two together, again with the chain rule, this becomes so this will then become j trace of so this is your delta j. Now these derivatives of kinematic quantities that we have derived so far are very important for what we are going to do next, and please derive them yourself and follow the derivations, and I will put up an exercise on Mookit, and please do that exercise as well.